Good morning, everybody, and today is our second lecture, and this is going to be a lecture on Cryptomania.
Sorry, I'm just fighting with Zoom. Sorry. Okay, now you can, I think you can see everything, except I can't see you, but that's okay. So welcome. Now, today is our lecture 2 on Cryptomania. So what is Cryptomania? Cryptomania is the second one of Impagliazzo's 5 possible worlds. So last time we talked about one-way functions and minicrypt. And we saw definitions of security for symmetric encryption, one-way functions, pseudorandom generators, pseudorandom functions, block ciphers. We did a lot. And a very important concept that we covered last time is the concept of indistinguishability. So indistinguishability is when you cannot distinguish that message 0 was encrypted from the situation when message 1 was encrypted. And we also covered why one-way functions are necessary and sufficient for symmetric encryption. So minicrypt is the world that we covered in last lecture, and that's everything you can construct from a one-way function. So that's one of Impagliazzo's 5 possible worlds. So this is a picture of Russell Impagliazzo, who came up with the idea that we don't know which of these worlds we live in. So just to recap, Cryptomania is the world that we're going to address it today. It's a world in which more sophisticated cryptography is possible, not just one-way functions, not just things that you can construct from one-way functions. And one-way functions exist, but there's more than just one-way functions. And the most important, like the important example of a Cryptomania resident that we're going to cover today is public key encryption.
So just a question about terminology. So minicrypt, so mini comes from the fact that it's minimalistic, kind of minimalistic setup. Okay.
Exactly. So you cannot have any cryptography, like any encryption, without one-way functions. So minicrypt is like, this is the minimal thing that you need is one-way function, and everything you can get from one-way function is minicrypt. So today we're going outside of minicrypt to public key encryption. And the reason that it's outside of minicrypt is that Impagliazzo and Rujic showed that you cannot build public key encryption just from a one-way function in a kind of a black box way where you're not actually looking at how the one-way function works, but you're just using it as input and output. Okay, so that's kind of the big picture plan for today, but we're going to do lots of things along the way. But first, remember our methodology. So in order to achieve something, anything in cryptography, the first thing we need to do is give a definition of security, like what do we want? The second step is we give a construction. So preview, to construct public key encryption, we will use one-way functions, but they will have to have something extra. And we will also use zero-knowledge proofs. And then we give a construction and we must prove that it's secure. And actually, these proofs of security are usually very long and involved and complicated. So I'm going to give you kind of a very quick version of that. So, but, you know, hopefully that's still going to give you a good flavor. Okay. So in more detail, the plan for today, I'm actually going to start with zero-knowledge proofs. We're going to talk about definitions. It's still going to be a little bit high level construction, and especially the important thing for public key encryption is a non-interactive flavor of a zero-knowledge proof. And then we're going to get to public key encryption. Okay. All right, so let's talk about zero-knowledge proofs. So what's a zero-knowledge proof system? So let's say we have 2 participants. We have a prover and a verifier. And the prover has some theorem X. Any statement, any mathematical statement, we can think of it as a theorem. And the prover knows the proof of the theorem. Whereas the verifier only has the theorem, doesn't know the proof. And we want the prover to convince the verifier that the theorem holds. So one obvious idea for how to do that is to just say, here is the proof. Now you can verify it for yourself. But that's not what zero knowledge is about. In zero knowledge, you want to keep you want to keep it fun. You don't want to just give away the proof. You want to say, yes, my theorem holds, and why don't you find the proof yourself? So you don't want to give it away. So the question is, how do you convince, so let's say you are the proofer, how do you convince your friend, the verifier, that your theorem holds without revealing anything about the proof of this theorem? So that's the question, and the zero knowledge proof is the answer to this question. Okay, so we're still kind of warming up. So let's have a crash course into zero knowledge proofs. But before we do that, here is a puzzle. So it's a very, hopefully, rather easy puzzle. Here's a graph. And my question to you, and feel free to interrupt and volunteer ideas, is how do you color the vertices of this graph? So these guys in 3 different colors, red, green, or blue, such that no edge is monochromatic. No edge connects vertices of the same color. So let's try to color this graph in this way. So for example, we can color this vertex red. This one can be green, right? Because it needs to be a distinct color, not the same as this one. Then this one, well, this one already had a red neighbor and a green neighbor, so it has to be blue. Now we need to color this one. This one only has a red neighbor, so let's color it green. This one has neighbors that are both green and blue, so let's color it red. This one has neighbors that are green and red, so let's color it blue. And now we're stuck because this guy has neighbors of all colors, so all the colors are taken. So here's a question. Hopefully you can see immediately how to fix this. Is there another way to color this graph so that so that it is 3 colorable? Like how can I change this coloring a little bit so that it's colored properly?
Yeah, we can change a second green for a blue.
Yes, exactly. And then problem solved. Okay, yes, so let's try to do that. This one is fine because it only has red neighbors, so it can become blue. And then this last guy, it has a blue neighbors and a red neighbor, but it doesn't have any green neighbors, so we can color it. Okay, good. So that's graph. That's like the problem, how to 3 color a graph. Okay. So, and of course, not every graph is 3 colorable. So here's a graph that's not 3 colorable because you have to color these outside triangle in 3 distinct colors. And so this guy inside we're stuck. We don't know how to color. Okay, so now imagine the scenario where you have a graph, and for the purposes of this explanation, this is the graph we're going to use. So we already know how to 3 color it. But you can imagine that maybe our input graph is much bigger, much more complicated. So you cannot just easily find the 3 coloring. But for illustration, I'm going to use this graph. And here is prover who wants, so he's acting as the prover, and we're all, let's think of ourselves as verifiers. So he wants to convince us that his graph is 3 colored. Okay. How can he do that? Well, one easy, oh, there's a comment in the chat. Okay, good. Yes, exactly. I agree with what's on the chat. So he can just say, here's how you 3 color it. And we're all convinced. We can easily look at this graph and verify that it's properly 3 colored. But what's the fun in that? If he does that, then he gives away the solution. So let's try to do it in a way that's more interesting than that. So how can he do that instead? He can kick us out of the room. So like now pretend that we can't, he's doing something with this graph, but we can't see it because he's kicked us out of the room. And what he's going to do is he's going to privately color all the vertices of the graph in one of 3 colors. And then he's going to cover it up. And I'm just going to use this visualization that he's covering it up with paper cups. And then he invites the verifier back in and says, you can check just one, I'm going to let you check one edge. And you can check any edge you want and make sure that it's colored properly, that it doesn't connect two vertices of the same color. So for example, this is the edge you want to check. Okay, let's check this one. So he opens just the paper cups that correspond to the edge that's picked by the verifier. Okay. But now the question is, how do we make sure that the verifier has better odds of catching him? So if the graph is not three-colorable, it might be the case that it has to be the case that there's some edge somewhere that's colored improperly, but the verifier's odds of finding it are quite small because if he's choosing an edge just at random, he most likely will not pick that one. So he will need to check more edges. They'll need to do more of this. So now let's say that the prover says, you want to check another edge. How do we allow the verifier to check more edges without learning any additional information? So the first idea, that's kind of obvious, is to say, all right, here, you want to check this edge? Fine. Here are the colors. But with this approach, we are revealing not just how a single edge is colored, but maybe like a whole region of the graph. So now the verifier is learning something else about the solution. So that idea is out. So we need to do something else. So the way we're going to do that is after the verifier has checked just this one edge, he must leave the room again. And now the prover gets busy. He says, this was my coloring. I can't use it again because if I use it again, the verifier will see some connections between colors of different edges. So I'm going to permute these colors at random. For example, whatever was red now becomes green. Whatever was green now becomes red, and the blue stays put, for example. So now that he has recolored the graph at random, he covers it up again with paper cups. Where did my prover go? Oops. And then he allows the verifier to come and challenge him to see the coloring of another edge. There we go. Okay. And if they continue this, I said 100 times, but for large enough values of 100, then eventually the chances that the prover can get away with lying, with claiming that the graph is three-colorable when in fact it isn't, become arbitrarily small. So as the more times we repeat, the smaller the chances. And it's you can use a Chernoff bound.
We have convergence and probability.
Sorry, what?
So do we have a convergence and probability there?
Well, it becomes, so if you, what's your favorite, like how low do you want the probability to be? So let's say that you want the probability to be constant, right? Mm-hmm. You want the prover to only get away with showing you with a false claim with constant probability. Then you need to repeat. So you use your favorite inequality from probability theory to check that. Don't take my word for it. But if you repeat a linear number of times, then a linear in the number of edges in the graph, then the probability that the prover can get away with cheating becomes constant. And then you repeat it some more, and then it goes down even more. Okay. Okay, so this is kind of a simple protocol, which is why I'm presenting it to you. There are other protocols that are less simple, but more efficient. And this protocol is due to Goldreich, Micali, and Wigderson from 1986. And if these names might sound familiar, Goldreich is the author of the book that I'm referencing. Micali, I talked about him in last class. He's a Turing Award winner. And Wigderson won the Fields Medal, I think just this year, right? Anyway, so these are kind of important. Maybe not. I forget what he won this year. Mm-hmm. Something he won this year that's very important, and I forget.
And a computer science award in math. Yeah, I have a question. Is it specific to this particular three-colorability problem, or it could be?
No, that's a very good question. So the three-colorability is an NP-complete language. So any statement you want to prove, if it's a statement about membership in an NP in a language in NP, you can reduce it to three-colorability, and so you can prove it as zero knowledge. And you don't need to use this proof, and you don't even need to for languages that we care about. Often there's a direct proof system, so you don't need to reduce to three-colorability. There's a direct proof, but it's just more, it's harder to explain. So this is the one that's easy to explain.
It sounds like for this to work, the proof kind of has to be very constructive. So it's some restriction on the type of proof that works. Is this what you're saying? Like
what do you, oh, you mean if you have a theorem and proof? Well,
yeah.
it has to be like a machine checkable proof,
I see. Mm-hmm.
right? Otherwise
but for any kind of machine checkable proof, this type of stuff can work.
Yes, that's right. Yeah. Okay. So another question that I guess you didn't ask, but that was probably your next question, is do you actually need the paper cups? So I explained this protocol using paper cups. And of course, that's not like how a communication protocol can work in practice. Like, it's not like we use physical room and physical paper cups. And instead we use, instead of paper cups, there's a cryptographic primitive called cryptographic commitments. And I'm not going to be very formal in explaining it, but just for this specific application, in this specific case, in order to commit to a color, so we can use our friend one-way permutation. So remember, we covered one-way functions, one-way permutations last time. So let F be a one-way permutation, and let B be its hardcore bit. So it's a Boolean function. And if you want, so let's say that we have three colors represented by strings 0, 0, 0, 1, 1, 0. So in order to color this vertex V with one of these colors, we pick random x1 and x2. This should be index, sorry about that, that are appropriate length for this one-way permutation. We evaluate our one-way permutation on x1 and x2. Then we have this mask. This is supposed to be concatenation. So you take this Boolean function of x1 and the Boolean function of x2, and you use this resulting 2-bit string to mask the true color. And then you just say, here is how I colored this graph. I'm not going to show you the colors in the clear, but I've masked every color, but but now you have these y1 and y2, so I cannot change my mind about what's inside this. I cannot change my mind about how I colored the graph, because the moment I tell you my y1 and y2, they uniquely defined x1 and x2, and therefore they uniquely define the color. But showing you this masked color doesn't tell you much about the color of V, because this bit is a hardcore, so you cannot compute this bit B of X from F of X. Okay, and I think there might be something on the chat. Oops. Let me see if I can see the chat. I don't understand. Oh, there we go. Yes, there's something on the chat. Can the adversary actually restore the colors of the many repetitions? Aha, that's exactly the point. Yeah, so the reason the adversary cannot restore the colors after repetitions is that before we repeat, we recolor the graph in a random permutation of the original colors. So this is what
yeah, so that's what I'm asking. Basically, if you repeat querying the same edge multiple times, and the prover changes the colors, we will eventually get the matching set of colors. So for example, we start with one edge, get some colors, then we continue to the adjacent edge, query it until the common vertex is of the same matching color. Then if there is a triangle between the first and the third vertex, we query that edge until it becomes matching.
Okay. So this won't work because every time what the verifier sees is he sees two random colors that are picked at random and independent of any previous colors that he saw. So he just sees, okay, I see two random colors. I see that they are distinct. They were picked independently of any other coloring that I've seen before, and so they don't tell me anything new. That's the idea, and I'm going to come back to that in a little bit. Okay, and Ludmila is way ahead of us. She's already suggesting that there needs to be a simulator, so let's get to that. Okay, all right, so let's get to what it actually means. Okay. Good. So let's think about a more formal definition of what is a zero-knowledge proof system. So first, remember, like, what are we actually proving? I said theorem, and then I said, oh, we're proving that a graph is three-colorable. Is that a theorem? So that tripped Andre a little bit. So let's recall for a moment, what's a language in NP? So let's pretend we're always proving membership in a language in NP. So language in NP consists of string X, such that there exists a witness for the string, such that some polynomial time witness verification algorithm is going to accept X and the witness. So for example, three-colorability is a language in NP because it consists of graphs G, which of course you can always represent a graph using a string, such that there exists a way to assign colors to the vertices so that each edge is colored in two distinct colors. All right. So our proof system is always going to be for some language. And for the purposes of cryptography, we always consider proof systems for languages in NP. Okay. All right. So that's the first thing that's important to kind of formalize. The next thing that's just kind of notational thing to make it easy to understand what's happening here in this definition is that, remember, we have two parties that are talking to each other. So if we have two interactive algorithms talking to each other, I'm going to have this notation, when I underline one of the parties, that means that's the party whose output I care about. So sorry, this is kind of a lot to read, but it's nothing very, very interesting. Okay, good. So now I'm ready to give the definition somewhat more formally. So let's say that we have a pair of algorithms, an algorithm for the prover and an algorithm for the verifier. And they constitute a zero-knowledge proof system for a language L if, first of all, there are other proof systems, but for the purposes of cryptographic proof systems, we really care that the verifier be a probabilistic polynomial time algorithm. And probably, in order to be useful for cryptographic constructions, we also need the prover to be a probabilistic polynomial time. So that's kind of a prerequisite for this whole thing to be interesting. And then the actual properties are completeness, soundness, and zero knowledge. So completeness means that if the prover and verifier follow the protocol, then the verifier accepts. So if they're given an X that's in the language and the prover is also given a valid witness and they follow the protocol, and the verifier is going to accept. And I defined it here as like perfect completeness, as in he always accepts. You can relax that, but this is the, let's stick with the easy stuff. Then there's the soundness. So soundness is something that we cannot actually have perfect soundness and zero knowledge for non-trivial languages at the same time. So I have no choice but to define soundness probabilistically. So soundness says if X is not in the language, then no matter what the prover does, obviously he's not going to be following the protocol because the protocol is only for when X is in the language. But doesn't matter what he does. The probability that he'll be able to convince our verifier is at most epsilon. So soundness epsilon means this probability is epsilon. So we talked about it a little bit in our three-colorability proof system. I argued if the graph is not three-colorable, then there has to be, then no matter what the prover does, there has to be an edge there somewhere whose endpoints are the same color. So the verifier is going to have, the verifier will discover that with probability 1 over the number of edges. And if you repeat this sufficient number of times, then you can drive that probability down arbitrarily. Okay, so that's soundness. Everybody's with me so far, so good. Let me check if there are any comments. Except I don't know how to do that. Okay, no, okay. Sounds like you guys are either completely lost or totally fine. So speak now if you...
We are fine.
Okay, good. So now the interesting protocol is zero knowledge. I mean, interesting property. So that's what Ludmila was alluding to. So zero knowledge property says, no matter what the verifier does, so the verifier might not follow the protocol either, there exists a simulator algorithm. And let me first tell you what the intuition is. The simulator algorithm is trying to capture whatever it is that the verifier is learning from the prover, except that the simulator algorithm doesn't have access to the prover. So the simulator algorithm is saying, look, whatever is learnable from this prover, I can just figure it out without the prover. Just as long as X is in the language, I'm going to produce an output that is indistinguishable. That's our old friend from Monday, indistinguishability. I'm going to come up with something that's indistinguishable from what this malicious verifier would have come up with, would have cooked up after talking to the prover. All right, so now let's look at the more formal version of this definition. So for any verifier, and there exists a simulator, I'm going to call him SimV here, such that for any X in the language, the output of this simulator is indistinguishable from the verifier, the malicious verifier's output as a result of talking to the honest prover. So I guess it's the same as what I just said. So, and again, the meaning is that whatever V star learns from the prover, it can just learn by just running sim V star without any access to the prover at all. And it seems counterintuitive that this should be even possible because, well, if the verifier learns nothing from the prover, then maybe you can only do this for trivial languages. So what's the catch? How can the simulator do something more than what the verifier can do? How can the simulator, how can this work for a non-trivial language, I guess is the question. And so the simulator needs to have something extra, some extra power that a prover or a malicious prover won't have over the simulator. So remember, you shouldn't be able to trick the verifier. Like if the verifier is honest, you cannot trick him into accepting something that isn't in the language. So, so we need to make sure that the zero knowledge property doesn't contradict the soundness. And so the simulator has this extra power where he knows something about the internals of the verifier that isn't available to an actual prover. So for example, the simulator can kind of run the verifier, and then if he isn't getting something that he likes from the verifier, he can reset the verifier to a previous state. So that's one example of an extra power that the simulator has over the verifier. Okay, so now that I've given you the definitions, and there I've repeated them right here. Let's convince ourselves quickly that the protocol we just saw for three colorability is in fact the zero knowledge proof system. So the running time, I've hand waved like crazy. This running time is really slow. As I said, there are better protocols, but this one is simpler. But it's polynomial, which, because this is a very theoretical lecture, is good enough for us for now. So running time is fine. Completeness is also fine. I think you are convinced. Soundness, we've already argued. So the only thing that's left to do is to show that this zero knowledge property holds. So I need to give you the simulator for this proof system. So I'm going to give it quickly. So here is how the simulator is going to work. So this is where, who was asking this question before? Was it Misha, who was like doubting that this is actually zero knowledge? Chat.
Yeah, it was me, Maxim.
Oh, Maxim. Okay, sorry, I wasn't paying attention. Anyway, so now this is the point in time, Maxim, where you might or might not see why I'm saying that it's zero knowledge. So here is my description of the simulator. So the simulator, before he even runs the verifier, so he has the code of the verifier, and the randomness of the verifier is fixed. And remember, this verifier is malicious, so it's not necessarily the verifier that comes with the proof system. It's an adversarial verifier. So before the simulator even runs this verifier, he guesses an edge. And he says, if this is the edge that this verifier wants to check, then I'm in luck. Otherwise, I'm going to have to try again. This is how he proceeds. Okay. Now that he's decided on which edge is going to be checked, and he might be unlucky, but he will be lucky with probability 1 over the number of edges, because he picks it independently of the verifier, and we can argue independently of what the verifier sees. Okay, now that he's picked this edge, he picks 2 random but distinct colors. So for example, red and green, and colors this edge using those colors. Okay? And then colors all the other vertices, the ones that nobody's ever going to ask him what these colors are anyway, but he's like, all right, everything else is red. So if the verifier were to check any of the other ones, he will not be able to proceed. So he's really gambling that the verifier will check just that edge E. All right, so now that he's colored the graph, he commits to all these colors and send this commitment to this malicious verifier V star. Okay? And by send the commitment, I mean he runs V star with these commitments. And then he says, okay, now V star wants to check edge E star. If the simulator's guess was wrong, he's in trouble. He needs to restart. He goes back to step 1 and tries again. Otherwise, he's lucky, and so he opens the commitments to the colors. So he does this until he finally gets lucky, and once he does get lucky, he opens these commitments to these colors and sends the openings of the commitments to the verifier V star. Then V star runs on that and, like, I don't know, does some computation, whatever V star wants to do, and produces an output. And now the simulator outputs whatever V star outputs. And I am claiming, and you're going to have to believe me because there's not a whole lot of time to, to doubt this claim. I am claiming that this simulator ends up with an output that is indistinguishable from the output of the malicious verifier V star. So I hope, Maxim, that answers your question for why V star isn't learning any patterns about what's happening in the graph. Okay.
But the question is, isn't it going to be then exponential? I mean, this algorithm will be polynomial time, because if we in the average case we can go over all the edges, and it's kind of exponential, if I'm not mistaken.
It's not exponential because there is a linear number of edges in the size of the graph, and the chances that we guess correctly is 1 over the number of edges. So Misha raised his hand. Misha, did you want to comment?
Oh, yes, I don't understand why are we talking about malicious verifier instead of malicious prover? And also, could you clarify or provide an example? What does output on the previous slide means? Output of interaction. What exactly is the output?
All right, sounds good. Let me backpedal if I. Okay. So
there was like a definition, I think, earlier of output.
That's right. So let me first talk about
advisory.
Who is malicious here. So for the purposes, so we need to consider both, like what happens when one party is malicious, like when one of them is malicious and the other one is honest, what can go wrong, right? So the soundness property addresses the situation in which the verifier is honest and he just wants to, but he only wants to accept X if X is in the language. And the prover might be malicious and is trying to trick him. So that was the situation we considered when we argued soundness. Now, when we argue zero knowledge, we have the reverse situation where the verifier is malicious and is trying to learn something he's not supposed to learn. So our goal for this protocol is that the verifier doesn't learn anything at all, other than he becomes convinced that X is in the language. And the verifier might be malicious. So he might say, I know I'm not supposed to learn anything, but I'm really going to try to get away with learning as much as I can. So that's why all the jokes about this lecture being zero knowledge can come tricky. Like, well, we're going to try to learn as much as you can, even though you're maliciously speaking too fast and I'm not conveying any information. Okay. Does that, Misha, did that
answer? Does it mean, I think the terminology was kind of confusing. Does it mean that because just trying to find the proof that only prover knows doesn't sound like something malicious, but does it mean that verifier wanna maybe impersonate the prover and then like say that I know the proof as well and then prove it to someone else?
Yeah, so we're not explicitly considering that as part of zero knowledge, but if the proof system is zero knowledge, then the verifier doesn't learn anything about the witness W that would allow him to then run a proof system with somebody else. So that's true. It kind of follows. You have good intuition there.
And what exactly the output is of interaction?
Good. So the output of interaction. So let's say that we have. Let's pretend that you and I are both algorithms, right? So you compute something and you send it to me. Then I compute something from what you just sent me and maybe some other inputs that I receive, and I respond with a message to you, etc. Eventually, I get a message from you, I compute, and I say, all right, now I'm done computing. I'm not sending you any more messages. I now know that I am done with whatever my task was, and I produce an output. Just like any Turing machine, right? The Turing or any algorithm, takes as input and it does some computation and then it produces an output. So an interactive algorithm does the same thing, but also is allowed to receive messages from the outside world. So by output, I just mean that. I just mean this verifier, he has an input, he gets some messages, in this case, from the prover. He computes on those messages, and eventually he says, okay, I'm done with my computation. Here's my output. So that's all that I mean.
So are we like exchanging the tape? Like you have a Turing machine and me, and we like one after one.
Yeah, it
run.
could be.
And
So
output is like the final state of that tape.
It could be that, like that could be an example of an output. So for example, the entire history of our interaction, like it could be that my output is my input, my randomness, all the messages we have exchanged. That could be an example of my output.
Okay.
Yeah. So the simulator's task is to create, is to output something that's indistinguishable from what the verifier would output as a result of its interaction with the prover. So now let me fast forward to the description of the simulator for this proof system. So in this case, the simulator kind of is prepared to respond to just that one challenge of this malicious verifier. If he guesses incorrectly, then the verifier does not produce any output, and neither does the simulator. Instead, if the simulator guesses correctly, he rewinds to step 1 and tries again. And he keeps trying until V star happens to challenge him on the edge that he's ready to open. And then he is in luck, and he responds to the verifier V star, lets him run to the end of his computation, and then outputs whatever V star outputs. All right, sounds like I've bullied you into accepting that as an answer. So let's move on. So, okay, so what did we just show? So we just showed that the protocol that I showed you before for 3-colorability is a zero-knowledge proof system. Okay. So now here's another theorem, which I'm not going to prove in all its glory, but I'm just going to... so this theorem is that everything that's provable, any language for which there is a proof system has a zero-knowledge proof system. And for the purposes of cryptographic algorithms, we only care about languages in NP. And since 3-colorability is NP complete, it's easy to see that any language in NP has a zero-knowledge proof system. Okay. Okay, so now it turns out I promised to show you how public key encryption works, kind of in general, the theory behind it. And for that, interactive proof systems are actually not useful at all. And what we want is non-interactive zero-knowledge proof system. So I'm just going to give you the definition. I'm not actually going to tell you how it works, but now that you've seen an interactive one, hopefully you have enough intuition. So in a non-interactive zero-knowledge proof system, there are 3 algorithms. There's an algorithm that sets up the parameters of the proof system. So it turns out that this proof system needs to have some kind of public parameters. And then there's a prover's algorithm that takes as input these parameters, the X and the witness, and produces a proof. And the verification algorithm that takes as input the parameters, the statement, and the proof, and either accepts the proof or rejects. And we also have, analogously to the interactive case, there's completeness that says if X is in the language and W is a witness, and the parameters are chosen correctly, and the proof is computed using the prove algorithm, then the verification algorithm will accept the proof. And there's soundness. So soundness means that for any adversary who's acting as a prover, if the parameters are chosen honestly and given to this adversary, and then the adversary says, here is my statement X, and here is my proof, the probability that X is not in the language and yet the proof verifies is negligible as a function of the security parameter. And then the security parameter lambda comes into this setup here. And then there is zero knowledge, which again requires that there exists a simulator which consists of 2 algorithms now. So the simulator is allowed to generate the parameters in some way that he somehow knows a trapdoor that corresponds to the parameters. And it also includes an algorithm that allows the simulator to simulate proofs. Okay, so, and what is the goal of the simulator? So the goal of the simulator is to create fake proofs for statements for which it does not know the witness. And these fake proofs need to be indistinguishable from the real proof. In other words, we have these 2 experiments, and in each experiment, I've defined these are the steps of the experiments, and then each experiment has an output. So the real proof experiment, we have parameters that are generated according to the setup algorithm, and the proof generated according to the prove algorithm with a valid witness for X. And then the output of the experiment consists of the parameters and the proof. And in the simulation, the parameters are chosen using the simulator, and the proof is simulated. So the simulator doesn't know the witness, only knows a trapdoor for these parameters. and then outputs the parameters and the proof. And the point is that of this zero knowledge property is that the output of the simulation experiment is indistinguishable from the output of the real proof. And I need to tell you something about this definition. This is actually a simplification of the definition that we need, and I'm sweeping a lot of things under the rug. The important thing about this, the important thing that I swept under the rug, because I don't want to spend time on it right now, but it's something to kind of keep in mind, is that we need to make sure that soundness still holds, even if the adversary can see simulated proofs. And how to formalize that is a little bit non-trivial, so that's why I chose to skip it. But that's kind of an important thing to keep in mind. So that's also an important property of a non-interactive zero-knowledge proof system. Okay, and then we have an important theorem by Feigele, Bedot, and Shamir, is that if trapdoor permutations exist, then non-interactive zero-knowledge proof systems exist. I guess I should say exist for all languages in NP. And note, a little problem here, I haven't actually told you what a trapdoor permutation is. But this is an important theorem to keep in mind, because now finally, 50 minutes into the lecture, we will see why they help us achieve public key encryption. But I haven't shown you how NIZKs work, and I'm not going to. I'm just telling you, trust me, they exist, they work. And you can see how they can be useful in practice. So in fact, right now is like the golden age of non-interactive zero-knowledge proofs. Like any cryptography conference is going to have a million papers on non-interactive zero-knowledge proofs with various flavors for various languages and as efficient as possible. So there's a lot going on in them, but I'm not going to show you any of that. I'm just saying they exist. Let's use them. Okay, so now let's talk about public key encryption. So what's public key encryption?
May I ask a small question?
Yes.
About completeness. In our definition, in completeness, honest verifier accept proof obtained from honest prover with probability 1.
Yeah.
Are there some protocols in which this probability is less than 1?
Yes. In the post-quantum world, like we thought before all of these lattice-based constructions came into existence, we thought, well, why wouldn't completeness, you know, it's not interesting to even consider the case when completeness is less than perfect. But unfortunately, we have to consider this case. If you want efficiency in post-quantum based cryptographic algorithms, then completeness is not 1, but it could be 1 minus negligible. So that's a good question.
And about extractor, do we distinguish?
Let's not go there. Sorry, because if we go there, then I won't have time to cover public key encryption at all. But maybe later, maybe in a little bit. Okay. All right. So public key encryption. So in public key encryption, we have the goal of public key encryption, and of course, I should have added citations. Public key encryption was an idea that's due to Diffie and Hellman, and the first algorithm to suggest how to do it, it was due to Rivest, Shamir, and Edelman, and that was, you know, back in the 70s. So it's by now real, like this is basically what jump-started the entire field, the entire academic field of cryptography is the discovery of public key encryption. So it's very, very important. And the main idea is that in order to encrypt, you don't actually need to have shared a secret with the recipient. It's good enough if the recipient's encryption key is public and everybody knows what it is. And so you just grab it from like some kind of a public directory, and now you can send the recipient an encrypted message. Okay, so public key encryption algorithm consists of 3 algorithms: key generation, encryption, and decryption. And the key generation outputs 2 keys. One is the public key for encryption, and the other secret key for decryption. And encryption just needs the public key and a message in order to produce a ciphertext, and the decryption needs a secret key and a ciphertext in order to recover the message. And correctness for encryption means that for any proper public key, that's the output of key generation, and for any ciphertext that is the output of encryption, the decryption correctly recovers the message. So far, same as any sane person would define it, and the same as in the symmetric encryption case. So now let's talk about security. So if you remember, we already defined security for the symmetric case in which the encryption and decryption algorithm use the same key K. So the definition for the public key case is actually in some sense simpler. And the reason it is simpler is that we don't need the encryption oracle because the adversary can form encryptions himself. So he doesn't need to issue encryption queries. So what exactly does the security game look like? So we have the adversary, we have the decryption oracle. The adversary receives the public key. Then the adversary can form queries, say, okay, here's my ciphertext, and observe how the ciphertext, what the ciphertext decrypts to. Then there's a challenge phase in which a challenge ciphertext is formed, which is either the encryption of M0 or the encryption of M1, and the adversary doesn't know which one. So there's an experiment with the bit B equals 0 and the one with B equals 1. And after that, the adversary can ask more decryption queries, just as in the symmetric case, with the only restriction is that he shouldn't be asking exactly C star, because otherwise it's too easy. And he receives decryptions for these queries. And then finally, he says, all right, here is my output. Okay. And our goal is to make sure that in our scheme, the probability that in our scheme, the outputs, the case when B is 0 is indistinguishable from the case when B is 1. And the way we're going to capture it, again, is by just measuring the probability. What's the probability A outputs 0 and B is 0? What's the probability it outputs 0 and B is 1? And we want these probabilities to be negligibly close to each other. Same exact as in the symmetric case. All right, so now we know what we're trying to construct. So let's try to construct public key encryption. So how are we going to do it? So our key generation algorithm. So this is our first attempt, which is going to be a little bit broken. So then we'll have to fix it using non-interactive zero-knowledge proofs. So a key generation algorithm outputs as its public key, it's going to output a one-way permutation with hardcore bit B. But this one-way permutation is going to have a special property that it has a trapdoor. So there's a way to find an F such that it has a trapdoor, and there's an efficient way to also compute its inverse if you know the trapdoor. Without the trapdoor, it's a one-way permutation. So that's what a trapdoor permutation is. So for example, RSA is a trapdoor permutation. That's what our key generation algorithm does. And then encryption, so just for simplicity, let's pretend that the message is just 1 bit. So to encrypt, you pick a random X from the domain of our one-way permutation F. And the ciphertext C is F of X and B of X, which is the hardcore bit of this F, XORed with the message M. So remember, M is only 1 bit, so that this is just 1 bit here. So that's how you encrypt. And then to decrypt, you take this F of X, that's the Y, and from it, you recover X because the decryption algorithm has access to the trapdoor that allows it to compute the inverse of F. And then you can just recover M by taking the second, this bit of the ciphertext and XORing it with B of X. Okay, so I'm claiming that this construction is broken. So why is it broken? So correctness is easy to see. So correctness is not where it's broken. So, so is it secure? So first, and because I'm out of time, I'm not actually going to ask you to pause and think. But if you think for like a minute, you will see that if A does not have access to the decryption oracle, then actually this construction is secure because of the security of the trapdoor permutation and because B is its hardcore bit. So without, let me just go back here. So if all you get is f of x and b of x XORs the message, then b of x, because it's a hardcore bit for this one-way permutation, b of x acts basically like a one-time pad, like a random pad, and masks the message just fine. So if that's the only thing you see, then the scheme is secure. However, of course, the adversary actually does have access to the decryption oracle, because last time I've argued that it's very important that it be able to observe lots of other things happening in the system and not just the challenge ciphertext. So if he can have access to the decryption oracle, then here's how he can break the system. He forms his ciphertext. So let's say C star is the challenge ciphertext. So it has this Y star and this bit U star. So what the adversary can do is form this query in a clever way. He keeps Y star as before, but then U star, he negates it. He XORs a 1 to it. Then he receives the decryption M and negates the decryption. And that's it. Now he correctly recovers the message. So that's why this way is broken. So now let's fix it using non-interactive zero-knowledge proofs. So the way to fix it is the public key now consists of the parameters for the non-interactive zero-knowledge proofs and two trapdoor permutations, F1 and F2, with the hardcore bit B. And the secret key can just be the trapdoor for one of them, doesn't have to be both. Okay, and then to encrypt, basically it's the same as encrypting twice with the scheme that I just showed you. So you have a C1 that uses F1 and a C2 that uses F2. And then additionally, you compute a proof pi that these ciphertext C1 and C2 were formed for the same exact message M. So that's how you encrypt. And then to decrypt, you verify the proof pi, and then you reject if it doesn't verify. And if it verifies, then you recover, just as before, you recover X1 from Y1 using the trapdoor that allows you to compute this F inverse. And then you XOR this U1 with the hardcore bit of X1. Okay, so now I need to argue why this actually satisfies security. The correctness, I think, is easy to see. Okay, so I'm actually out of time. Andrei, is it okay if I spend a little bit more time just explaining why this fixes the whole thing?
Sure, of course.
Okay, thanks. So, so in this proof of security, and this is going to be a short sketch of the proof. The actual proof is much longer. We're kind of going to show that the game, when the message is 0, is or the experiment where the message is 0 is indistinguishable from the experiment in which the message is 1 by kind of altering the terms of the experiment, altering things slightly in such a way that every time we make a little change, we can argue why it's indistinguishable. And the real way of doing it is by giving you a reduction to some property of the underlying building blocks, but I don't have time to do the reduction. I'm just going to tell you what these games are. Okay, so the first game is our security experiment when the message is 0. So what is in this experiment? I don't know if you remember, I showed you like a second ago. In this experiment, we have a challenger that when the adversary sends it encryption queries, the challenger responds to them, decrypts them, and he uses the inverse of F1 in order to decrypt. Okay. And then also the challenger forms the ciphertext, the challenge ciphertext, by encrypting the message M equals 0. So this challenge ciphertext is going to consist of C1, C2, and the proof. And C1 is F1 of X1, and B of X1 XOR the message. Okay, is everybody with me? This is just the security experiment when the challenge ciphertext is 0. Everybody with me? Okay, nobody's saying anything or raising their hand, so I assume that this is fine. Okay, now I'm going to change this game a little bit. So, oops, wait, what did I just do? Oh, okay, I haven't changed it. I just plugged a 0 there because M is 0. Okay, now I'm going to change it a little bit. So now I've changed it a little bit so that our parameters, our public key is slightly different. We have parameters here that are actually sim parameters. So remember, the parameters in the scheme are output by the setup of the non-interactive zero-knowledge proof system. Here, I've changed the game so that instead of those parameters, we have parameters that are output by sim setup, by the simulator. And also, I've changed it so that instead of producing a real proof that C1 and C2 correspond to the same bit here, the challenger produces a simulated proof. But other than that, it's the same. Everything else is the same. So this game, with this slight change, is indistinguishable from game 1 because of the security of the non-interactive zero-knowledge proof system, specifically because of the zero-knowledge property. So if we had actual time to do it properly, I would show you a reduction. I would say, well, if you have an adversary that can distinguish game 1 and game 2, then we transform him into an adversary that can distinguish, that can break the zero-knowledge property of the underlying proof system. Okay. So next game, things are slightly more interesting because not only are the params output by sim setup, just as in game 2, but now our challenge ciphertext is kind of mismatched. It's nonsense. We still have 0 in the first half of it, but now in the second half, we use a 1. Okay, and we've simulated the proof. And it's indistinguishable from game 2 because this part, you know, in a perfect world, I'd show you in more detail because it's slightly non-trivial, but basically because of the security of the one-way permutation and the hardcore bit B. Because you can somehow hide, like you can have a challenge, like let's say that your task is to break the security of the hardcore bit for F2, then you could somehow massage this so that the adversary who distinguishes 2 and 3, you convert him into one that breaks the security of this hardcore bit. Okay. Now the next game, the ciphertext is still mismatched, but the change is that when you have decryption queries, you use F2 instead of F1. Okay. And this one is indistinguishable from the previous one because of the soundness of the non-interactive zero-knowledge proof system, even after seeing a simulated proof. And again, it's true, but like it's not immediately obvious. There's some but anyway, there is a reduction. Trust me. Okay, and then the next one is we still have simulated parameters, but now there's no mismatch. Both of these are ones, so we've converted both of them to ones, and we're still using F2, the inverse of F2, in order to decrypt. And this is indistinguishable again because of the security of the one-way permutation and the hardcore bit. And then the last change is the last change, second to last change, is now we've switched back to the correct parameters, not the simulated parameters. But we're still using F2 for decryption queries. But other than that, this ciphertext looks correct, looks like a ciphertext is supposed to look. There's a C1 and a C2 and a proof pi produced by the correct prover that they correspond to the same message M. So the only difference from the actual security experiment with M equals 1 is that F2 is used for decryption instead of F1. And this is indistinguishable from game 5 because of the zero-knowledge property, because of the sound, actually, I think it's because of the soundness. Yeah, it's not because of zero-knowledge, it's because of the soundness of non-interactive. No, never mind, because this one's because of zero-knowledge. Yes, this is because of zero-knowledge. And then the last one, we switched to using F1 for decryption. And here the soundness is what's important, because the soundness guarantees that it doesn't matter whether we use F1 or F2, they're the same. Okay, so this is very, very quick outline of how the security, this proof of security would work. So This is what I've advertised for today's lecture. I've covered zero-knowledge proofs. I've covered the definition of public key encryption. I told you what a trapdoor permutation is, and we've constructed public key encryption from non-interactive zero knowledge and trapdoor permutations. And it's a very theoretical construction, so nobody would use it in practice because it's very inefficient. But what it does tell us is kind of like, what would a secure public key encryption scheme look like? So this hopefully helps make sense of constructions that are used in practice. So in the last minute that I don't have, let me just see why it helps. So the intuition here is that in order to form a ciphertext, you somehow have to know the message. That's the point of this construction, is that you need to know the message, because you construct the ciphertext by encrypting it twice and by proving that you've encrypted the same thing. And if you didn't know which message, if you just try to construct the ciphertext some other way, you wouldn't be able to do that. So the way that this comes in, for example, so this is RSA OAP, so that's a very widely used public key encryption scheme. And the way it works is the public key is just one trapdoor permutation F. And to encrypt the message, first you encode it. So you get this encoded message EM. And the way that you encode it is you put your message here, then you pad it with some zeros. I'm not sure what this hash of L is, but there's some, I think there's like a random something they call seed. This is like a random value, and then hash of L is like everything like this, and the message M is you put it here. Then this, don't worry what these things are, but this is like some kind of a way to make sure that this resulting encoding, it's distributed, it's kind of almost uniform in the space, but from it you can recover the message back. And it turns out that then this requires a lot of analysis of this OAP, so I'm not going to pretend to do it like on the fly right now. But it turns out that the only way that you can create an encoded message that then decodes to something with this proper padding and a proper hash of L is if you know the message M itself. Like there's no way to even compute it without knowing M. So in some sense, what the RSA OAP is doing is it's taking the place of that proof, of the proof that it's the same message, that this is the message you already knew at the time when you formed the ciphertext. So that's hopefully helps you make sense. Like if you've ever seen some crazy complicated but very practical and efficient public key schemes, this might help you make sense of them. Like, why are they designed this way?